Hello everyone. In this module, we focus on unsupervised learning. Let's begin by recalling supervised learning, one of the most common approaches in machine learning. In supervised learning, we have a data set consisting of input features and corresponding labels or outputs. And the goal in supervised learning is to learn a function that maps inputs to outputs so that when we see new data, we can make accurate predictions. Supervised learning is very powerful, but it has a limitation. And this limitation is that it requires labeled data. Labeling data can be expensive, time-consuming, or even invisible in some cases. And this brings us to unsupervised learning, where we only have input data or input features, but no labels or outputs. And the goal here is not to predict, but rather to discover patterns, structures, or in general, hidden relationships in the data. For example, one of the main questions is things such as like, are there groups or clusters in the data just by looking at input features? If you want to write this mathematically, you can think of this as a data set shown here by D, where we have x1, x2 to xn. And recall that uppercase N denotes the total number of samples. And as mentioned, we do not have any outputs or labels in this case. So this means that during training or model fitting, if you want to put this in the context of supervised learning, we only have access to the data or feature metrics. And as always, the way that we write this is that we put each data point in one row. So in this case, x11, 12, 1D are the D elements or features of the first data point. And then the second data point is going to be in the second row, and so on to the nth row here. So we will have xn1, xn2, xnd. So this matrix is of size n by d. So we have n rows and d columns. And the goal here is, as we mentioned, to find some hidden relationships or structures in this data. For example, we can think of that as identifying which of these n data points are closer to each other, right? Or can we find abnormal data points that they are significantly different than normal data points? So there are a lot of interesting problems in unsupervised learning. For the purpose of this module, we mainly focus on clustering methods, which means that we want to partition the data, but the applications are really very vast. So one work, for example, I wanted to highlight here is that we can think of like, unsupervised learning in the context of analyzing MRI brain scans. So obviously one approach is that when we get these raw MRI scans or images to label people as, for example, in this context as healthy or different stages of Alzheimer's, but this costs a lot of money, right? Because you need to ask some experts, some physicians, specialists to label these images or scans. And therefore, it is really nice if we can sort of like automatically group these brain scans into multiple groups, depending on the context of the problem. So I just did a quick Google search and I found this very recent paper published in 2024 where they talk about different machine learning methods that they use to analyze MRI brain scans. So this is obviously something if you're interested in learning more, you can see what, machine learning methods have been used. Some of these are techniques that we're going to use or learn later on in this course, but overall, this shows you the importance and significance of unsupervised learning. And as mentioned, the most important, I would say, or the most popular type of unsupervised learning is definitely clustering, where the goal is to partition the data set into clusters or groups in such a way that data points within the same cluster are more similar to each other than those in other clusters. And here is the big problem in general, that we do not have a universal definition of a cluster, right? So if we have like, let's say a two-dimensional space, we can define a cluster as like circles and the data points inside that circle, or we can think of these as some sort of like elliptical shapes or some even more complex geometries. So therefore, the definition of cluster is very much wide open. And depending on the way you define these, will end up with different clustering algorithms. And that's one of the main goals of this module, to show you different ways of performing clustering. Depending on the application and the context, one might be better than the other ones. But overall, the best way to utilize clustering techniques is to understand a couple of different ways of defining these clusters or groups. And that's how we can be prepared to analyze a wide range of data sets. So in this module or course, we focus on three main clustering algorithms. So the first one is K-means clustering, which is really, really simple, but at the same time, it's very applicable to many different problems. Then we'll focus on density-based spatial clustering of applications with noise. I know this is a very long name. That's why this is known as DBS scan. So DBS scan is a clustering technique, which is different than K-means clustering, and we will talk about it. And then something that is mainly coming from a statistical literature, and that's Gaussian mixtures, where you assume that each cluster is a Gaussian or normal distribution with a given mean vector and covariance metric, since we can be in hard dimensional spaces, and therefore you can see techniques from something very simple such as K-means clustering to something that is more mathematically involved, including Gaussian mixtures. The other thing that is very important is that although clustering looks very much like classification at the first glance, because we're trying to assign labels or categories to data points, there are significant differences. And this shows up especially when you want to uh, evaluate clustering techniques. And in general, when you want to evaluate a clustering technique, you can use internal measures or external measures. And the reason that we distinguish between them is that in internal measures, we do not even need the ground truth output. So to make this very clear, we never use labels or outputs for training clustering algorithms. So during the training stage, we always assume that we only have input features, no labels. However, during the evaluation stage, you can assume that you have the ground truth outputs, and that probably is a good way of evaluating the performance of a clustering algorithm if you have that information. And in many cases, we do, since we're working with data sets that they are already labeled. However, in many cases, we do not have access at all to any labels. If we do not have access to any labels, that's why it's called internal measures. And these things are based on cohesion and separation of clusters, meaning that when we have data points assigned to different clusters, do we have clusters that are very coherent and also well separated from other clusters? And one very popular measure here is silhouette coefficient. And then for external measures, there are obviously different ways of analyzing the alignment between the true labels, where we have in our ground truth data set, and also the predicted clusters. And one approach is this thing known as normalized mutual information, which is a very nice technique. And the reason I like this is a metric which is from 0 to 1, 1 being the best, meaning that higher scores are better. So these are all the things we cover in this module, but right now we're going to start with K-means clustering and trying to show you some of the main assumptions, and in particular like loss function that we use for K-means clustering. Because whenever we talk about any machine learning method, whether it's supervised, unsupervised, one thing which is very, very important is to understand how we quantify errors and how we aim to minimize these errors. And if we know this, regardless of sometimes we may not focus completely on the ways that we can solve optimization problems because it's beyond the scope of this course. But it is very important to understand the loss function that we use to be able to perform k-means clustering. So when we say k-means clustering, the reason that it's called k-means is because we assume that we have k cluster centers or representatives, right? So we said that we want to divide the data into k groups or clusters, and each group has a center or representative. We show this using this mu k. And mu k is indexed from 1 to uppercase k. So uppercase k is the total number of clusters, and the small k, it shows the index for each cluster. And obviously, since we are in a d-dimensional space, since our feature vectors are in d-dimensional space, these cluster centers are also in a d-dimensional space. And the idea is very simple. So if we have these cluster representatives, which we show them using mu k, and bunch of data points xn, where n, the small n, is the index for the sample number. It goes from 1 to uppercase n. If you want to assign each data point to a cluster, you need to find the closest cluster center. So in that case, you're going to compare all Euclidean distances between xn and mu k's for different k from 1 to uppercase a k. And this gives us the kind of like the membership of this data point xn. So the way we write this, zn is one of these numbers from 1 to k, and that shows the membership of xn. However, the problem is a little bit more complex in the sense that we do not know the cluster centers or representatives. If we knew, yeah, we could just compare distances and everything would be great. So now what can we do? So we can form a loss function very similar to what we have done before. So we're going to find the distance between each xn. So n here is the sample index and the closest cluster center. So when I say mu zn, so the zn here is one of these numbers from 1 to k. So it tells us the closest cluster center to xn, and we're going to divide these two vectors, and this is sort of like our, if you want to think about these as residuals or the distance, and then we square this and we add them all together. And obviously we can divide by n if you want to normalize this, but it's not very common to do this when we are working with k-means clustering. Okay, so this is great, but the problem is that we do not have these mu's. So we have to kind of like be able to cast this as an optimization problem. So the way we do this, think about it this way. For each xn, each data point that we have, we can write this cluster center or representative as the summation over all mu k's, all the cluster centers, where we have the znk. So n is the sample index, and this k is the cluster index, which goes from 1 to uppercase k. And the way that we can define this is that let's put all these k different values for each n into a row vector. So now we have zn1, zn2, znk. So this is a 1 by k vector. And the way we do this, or we constrain this, is that only one of these values is 1, and the rest of these values should be all zeros, right? So this is what we call also as one-hot encoding, right? So what this means is that let's say if only zn1 is equal to 1, and the rest of entries here are zeros, so this means that this mu zn is technically mu1. However, if that 1 is in the second location, then we get here mu2, right? So this is very important, this structure here, that we only have one in here and the rest of entries are zeros. So since the ultimate goal is to write everything in terms of matrices and vectors like we have done before, because this is very nice. If we do this, we can handle any number of data points, any number of clusters, and we can efficiently solve problems. So that's where we are moving to. So we can put all these cluster centers or representatives in the rows of a matrix called M. So this M is a matrix that contains cluster centers. And mu1, mu2 to mu k. So this matrix has k rows, And the number of columns is the dimensionality of these cluster centers, which is D. So M here is K by D. So the next thing that we can do, so my goal here is to write this summation in terms of a vector matrix product. And the way we can do this is that now, if I multiply this vector that we only have 1, 1, and the rest of entries are zeros by this matrix, and remember this matrix has these rows mu1, mu2, mu k. So the way that this will work, since let's say only one element here is 1, if we do this multiplication, you're going to multiply 0 by the first row, then 1 by the second row, and then 0 by the third row, etc. So this is equivalent to picking the corresponding row of this matrix. And that's exactly what we call as mu zn, right? The corresponding cluster center for xn. So overall, what this means is that we can write that sort of like, residual that I mentioned before as xn, the original data point that we have, minus this summation over z and k mu k's, right? Because you have to pick one of these mu k's. And we can write this as a row vector times this matrix M. This row vector can be written as Zn to show that this is the nth row of Z. And this matrix M is fixed across all data points because we only need to have one matrix of cluster centers. And the next step here, really, to finish this analysis here, is to stack everything row-wise. So what does this mean? This means that now, if we have this for one xn and one row of the Z matrix Zn, we can put all these xn's together. And we already know what this is. This is the matrix X, right? Because this is the matrix that each row is one data point. And if we do the same thing for Zn, we get a matrix Z. So this is what is called the membership matrix. And here we have, so the size of this is n by k. So n is the total number of data points and k is the total number of clusters. So we need to have 1, 1 in each row that shows that xn belongs to which cluster. And then we multiply this by the matrix n, right? So this is x, z, and n. And we can either write this as the sum over the n for these individual data points. But again, the goal in machine learning is always to be able to write things as compact as possible. And we can do this using what we call it as Frobenius norm. So we have the matrix X minus Z times M. And since we are looking at this sum of the Euclidean squares, we can use Frobenius norm. So if you're not familiar with Frobenius norm, is very much similar to Euclidean norm for vectors, but here we going to find the sum of the square of all elements of a matrix, right? So Frobenius norm for a matrix is basically extension of the Euclidean norm for vectors. And therefore we have one summation over rows, like I, if we have like, let's say aij for a matrix A, summation over j, and then we square all these elements and add them together. That's the Frobenius norm. And therefore we do the same thing here too. So we're going to use our data matrix, trying to approximate this by Z times M, the membership matrix times the center matrix or matrix of all cluster centers. And we want these two things be as close as possible to each other. So if this difference is 0, that's perfect. But obviously we probably cannot find cluster centers that are perfect, meaning that they're all right on all the data points, right? We will have some scattering around those cluster centers. Okay, so now that we understand the loss function, the question is how we can solve this problem. So recall that we have two optimization variables here. So one is this matrix of cluster centers, M, and also the membership metrics. And that's what makes this problem difficult to solve because, although we don't go to all details here, but this is what is known as a non-convex optimization problem, meaning that it is very difficult in simple terms to find the optimal solution. And one of the easiest things we can do to solve this problem is one time to assume that M is fixed and try to find Z, because that problem is really easy to solve. It's just a linear problem here in some sense. And then the other one is to optimize M where Z is fixed. And each subproblem has, I would say it's better than saying that it's linear, it's better to say that's a closed form solution. That's what a better terminology is. So once we fix M, we can find Z using a closed form solution, and the same thing for the other side. And because of this, K-means clustering algorithm is actually an iterative way of solving this problem. We're going to, so since we want to optimize our Z and M, we have to find one of these two first, or at least initialize them. And it is very common to first initialize this matrix M. So meaning that we first select M centers. For example, you can randomly select K data points from the n given data points at random and call them cluster centers. Probably this is not a good set of cluster centers, but it's somewhere to start. So it's kind of like very similar to idea of like gradient descent. And then we iterate over the following two steps, right? We first try to find Z. So that means assign each instance to the closest cluster or closest cluster center. And then once we find Z, now we can update M, right? Because this means that now we know all the data points that belong to the same cluster. Let's update these cluster centers or centroids. And we'll then repeat this process. So again, given the new M, we're going to update Z, and then we update M. And we can repeat this process, let's say for 10 or 100 iterations. To show you how you can use this, so let's look at one example. So we import NumPy as NP, matplotlib. We're going to use a synthetic or artificially generated data here using scikit-learn datasets make blobs. So as this name suggests, so these make blobs allows us to create synthetic datasets that look like bunch of like blobs or clusters that we decide where the centers are, how separated from each other are, and also the density of data points, etc. So it gives us a nice way of creating synthetic data sets, and this is really nice to understand the basics of clustering techniques. And then scikit-learn has a module called cluster, which has this k-means. So very first thing that you want to use make blobs is if you want to specify the centers of these blobs. And in this case, we want to solve this problem in two-dimensional space because we want to visualize things. And this is the center for the first cluster, the second, third, fourth, and fifth cluster. You can also provide these standard deviations. So higher standard deviations means that we have the data points within the cluster are more spread out. So we want to make this interesting by having varying levels of scattering within each cluster. And then also the total number of samples that we want to have in this case is 2000. So let's plot this data set. And the way we do this is using a scatter plot. We plot the first dimension and then the second dimension. And we call these features x1 and x2. So this is the x1, x2. We have these 5 blobs or clusters. And as you can see, because I chose 0.4 and 0.3 for 2 of the clusters, you can see we have higher scattering or separation between data points within these 2 clusters. And then these 3 clusters on the left, they're really tightly put together. So this is a good example to see if k-means clustering is able to correctly or meaningfully partition this data set. But I have to also be very clear and fair here in a sense that this matches very well with the idea behind k-means because we do have these kind of like circular shapes, right? So this is One of those instances, K-means can perform very well because we do not have complex geometries. So in order to apply K-means, the very first thing you have to do is to specify the number of clusters that you want to recover. This is kind of like usually like a big problem. Why? Because in a real world problem, we do not know how many clusters we really have. So you have to identify this number. We will go through a couple of things we can do to figure out the right number of clusters, but still, like since if this is a really unlabeled data and we have not generated this data like here, there is no way to really know how many clusters we should have. So that's something that really depends on the context, application, domain expertise, etc. And the other thing is that since in this case, when we want to fit this k-means model, we do not have any labels. It is typically okay not to have a separate or dedicated testing set, right? Because we are worried about, you know, combining training and testing sets in supervised learning because we can just memorize the labels or outputs. However, we do not have labels or outputs here. So it is definitely not a big sort of concern that we may memorize structures since we have not given any information to this machine learning model. And since we mainly here want to look at the labels, for these data points when they're assigned to each cluster, I use fit and predict together. So you can use the typical approach of .fit and then .predict. That makes sense if you have different training and testing sets. But if you have only one set you want to train and then see whether the labels make sense or not, you can use .fit predict. And then the only thing we do here really that is different is that we're going to use these predicted labels as the color for these data points. And here's the result. So it actually works pretty well, right? So this shows us that all these data points belong to one cluster. These yellow ones and then these green ones. Obviously, you can see some small errors here, and this is something that we expect because we have a higher spreading of data across the space for these two clusters on the right. But overall, we are able to figure out the structure of this data. And in 2D, again, we can always visualize these and try to find these clusters visually. However, if you have like 3, 4, 5, 10 dimensions, you cannot do this anymore, right? Manually. So therefore, k-means clustering can be very helpful in those scenarios. However, here we resorted to a 2D problem because we wanted to make sure you can see the quality of these labels that we get from k-means clustering before talking about evaluation metrics in general. If you want to know where cluster centers are, you can do that. That's part of this because k-means right now is this object that has been trained or fitted. So now you can look at these attribute cluster centers and we get 5 rows here technically. So each row of this is one cluster center. So this is exactly that M matrix that we had before. And these labels are the Z metrics because it shows us the assignment. So this means that once we solve this problem, we find M, we find Z, we have this information. And if we want, we can also plot these cluster centers within our 2D space that we have. And you can see that that makes a lot of sense, right? So this is the representative for this cluster, representative for this cluster, and for the other 3 ones. So if you want to now, as you can see, use k-means model, so the best thing to do is to look at the documentation page, which is inside sklearn.cluster.KMeans. And the number of clusters is a very important, parameter, probably the most important thing you have to provide. By default is 8, but again, this is probably not a good choice for many problems. We have the way that we can initialize this k-means clustering algorithm, and I'm gonna talk a little bit about this. And the maximum number of iterations, how many times you want to update Z and M and in that order. And you can see that there are a couple of other options too. So like any other scikit-learn's implemented algorithm, definitely make sure to look at the documentation page, like for example, what .fit does, what type here we have to provide. So you can see here, like if you use .fit and if you provide even Y, it's ignored because we don't really need labels since we are doing unsupervised learning, right? And this is the fit underscore predict that we just used. So you can get a good sense of what methods and attributes we have, right? So you also get the set of all attributes if you scroll down or up here. So let's see, where are the attributes? Yeah, so the attributes are here. So we have cluster centers, that's what we use. The labels, if you want to find them. Inertia is very important. So inertia here is actually our loss function, the sum of squared distances of samples to their closest cluster center. That's exactly what we're trying to minimize. That's why it's called inertia, and that's why it's important to look at it after you fit your model to see whether this sum of squared distances is reasonable or not. So let's go back to our notebook. So one thing also I want to say is that when you use K-means clustering, although we use fit underscore predict to predict labels for the training data in some sense, you can still have a bunch of new samples or features and you want to predict the labels. So here, for example, we have a data point with coordinates 0 and 2, 3 and 2, -3 and 3, etc. And you can look at the labels, right? So it tells you that the first two ones are in the same cluster with the label 0, and the two other ones are in cluster 3. And that's something very important because these numbers, 0, 2, 3, these numbers that we get here, these things are automatically generated. So there's no ground truth output. So 0 here doesn't really make any sense because we don't even know what class or cluster 0 is. The only thing we know is that the first 2 points, this one and this one, they belong to the same cluster because they have the same label. But whether label 0 is this one or this one or this one, you have to actually find that information. And there's no very straightforward way of figuring this out. So in order to explain a little bit more how this numbering works and how initialization works, because we have to initialize that matrix M in order to use K-means clustering. So there are multiple ways you can solve this problem. So one approach is to randomly select some data points and say that these are my cluster centers, and hoping that you can improve this as you have more iterations over Z and M. And because of this, the performance really is dependent on the random starting points. And one of the arguments that you saw in the K-means documentation page was this n underscore init. So this is a very simple idea. If you know that the final solution depends on your initial solution, you can run the entire algorithm multiple times for different initializations and then see which one is the best one at the end. And when I say best one, usually is using inertia because that's what we are minimizing, the sum of the squared distances. And the one that gives you the best one, that's the one that you select as your final K-means model. However, I do believe it was around 2007 or 8 that we had this more, sort of like, a straightforward way of initializing K-means clustering technique. And that's what is known as K-means plus plus. And the only difference between K-means plus plus and the standard K-means is the way that you pick these initial cluster centers. And the goal is to pick them in a way that we can cover the entire space to the degree possible. So the idea is that first we're going to pick one data point as a cluster center randomly. But when you want to pick the second data point as the cluster center, you're going to define a probability score. And the way that this works is kind of similar to softmax score that we had before. So for each data point that you want to be eligible as a cluster center, you're going to find the minimum distance between that point and existing cluster centers. So that's why this is up to t minus 1. So this tells us how far we are from existing cluster centers. And then we normalize this by the sum of all these distances between all data points and existing cluster centers. And this gives us a number. So obviously, if the numerator is high, meaning that this data point xn is far from existing cluster centers, that might be actually a good choice to put a cluster center because it means that now we can try to see if we have any cluster there. And if this dt minus 1 is close to 0, means that we're already very close to an existing cluster center. So it's better not to really, pick out a cluster center very close to what we already have. So that's the idea here. So there's a way of finding these probabilities to make sure that we can have these cluster centers to be, to the degree possible, as far as possible, and that way we can cover the entire space. And this will hopefully help to get better convergence at the end. The other question with k-means is finding the optimal number of clusters. So in reality, we don't know this, parameter uppercase k. So how can we find this? So this is a little bit of like a hard problem. And the reason is that, well, as we find more and more clusters, obviously, we can have a smaller values of inertia, this sum of the square distances, because now we have more clusters. So in the extreme case, each data point, it's its own cluster, and that data point is the cluster center, and this inertia is exactly zero. So so like a trivial solution. But it is very sort of like, uninformative. And the reason is that now each data point is its own cluster. So obviously, we want to be cautious about adding more clusters in the sense that if we add more clusters, we want to make sure that this value here, this inertia, drops significantly. If not, then probably it's better not to add that extra cluster because then we lose the interpretability of our model. And therefore, this is why it's known as the elbow method or finding the elbow point. So this means that we can plot the values of inertia after solving k-means clustering algorithm for different values of k, and then see where we have a nice drop in this value and then kind of gets flat. I mean, obviously still we will have decrease because we're adding more clusters in inertia, but we'll see where it gets kind of like, pointless to add more clusters. So to try this idea, for different values of clusters from 1, as you can see here, to 10, we're going to set this number of clusters of k-means to a number. We can set the random state for reproducibility and initialization purposes, and then we use dot fit. And then for each model, we're going to look at the inertia at the end. And you see here's the result, right? So since this is excluding this 10, so it means that technically we're going from 1 to 9, and these are the values of inertia. So if you have one cluster, obviously this is probably going to give us a very high values of inertia. Adding the second cluster caused this huge drop in inertia, which is a good thing. 3 is also clusters kind of helps here, and 4. But after 4, you can see that we have now this kind of like very a small slope. So it still is a negative slope, as we said, because inertia values will get smaller as you add more clusters. You can do a better approximation, but it appears that it's not really significant anymore. And this is very interesting because for this specific problem, we had 5 clusters that we originally used to generate data. So what does it mean if k equals 4? So let's actually, look at this case and see how this partitioning of data looks like if we choose only 5 clusters or for like 4 clusters. And here's what we get, which is very interesting, right? And the reason for that is that we have this very nice cluster on the right, and then the second one, and then we have this top left one. But it appears that another way to think of this as a cluster is that since these two bottom left ones are very close and they're very tightly grouped together, they can be their own sort of like cluster or group. And that's why the idea behind this 4 here, right? So it seems that 4 is actually more meaningful because now you have nicer separation between clusters. These two are together, then you have a nice separation, and you have these two bigger clusters and they're separated as much as possible. So we can do 5 again, and you can see that in this case, actually, you can get different results too, right? So that's something I want to be very careful about, that this random state can really change the result, because when we use 5 this time, you can see that this cluster is divided kind of like in half, which is not necessarily a good thing, right? That doesn't visually make sense. So you can see that here, if I change the random state, now this makes a little bit more sense. And all this is because of the fact this K-means clustering is an iterative technique, right? So meaning that we start from an initial solution and then we try to make it better and better. So depending on where we start from, even when using K-means plus plus, you may find better or worse solutions at the end. So let's see with this random state, what happens if we choose 4 clusters. So in this case, you can see it seems to be more stable because these two are together, the yellow class, green, and this purplish color. But you can see that if I choose, for example, 2 here, this probably doesn't look that great, right? So K-means kind of like divides this whole entire space in half and says that everything here is one class, everything here is one cluster. So let's put this back to 4 because I think that's like the best result that we have for now. And you can see that in this case, we know the loss function for K-means clustering, how to implement it using scikit-learn, and how to find the optimal number of clusters. I hope you found this video helpful.